Okay, in this lesson, we will be using the concept of the derivative to analyze some properties of the function, and this will be in terms of whether the function is increasing or decreasing in some intervals of x values. Also in terms of whether the graph of the function is concave up or down in some interval of x values. So at the end of this lesson, using the value of the derivative, we should be able to determine whether a function is increasing or decreasing in a given interval of x values, as well as to determine on whether the graph is concave up or down in some given intervals of x values. Let us consider having a graph of some hypothetical function y equal to f of x as given by the orange curve. And let us try tracing the curve going from left to right, so that in this particular direction, tracing the curve, we go uphill, telling us that as we increase x values going from left to right, y values would be increasing. But in this section, we go downhill. As we increase x values, y values would be decreasing. Over here again, we go uphill, indicating that y values are increasing as we increase on the x values. In this section here, we observe that as we increase x values, y values are held constant. Let us now investigate whether a function is increasing, decreasing, or constant in some interval of x values denoted by x1 and x sub 2 by comparing f of x values. If it is observed that f of x1 is less than f of x2 whenever x sub 1 is less than x sub 2, then the function f is said to be increasing in the said interval. This can be illustrated by this graph given, where the blue graph indicates the curve of the function y equal to f of x. Notice that as you sketch the curve, or as you trace the curve from left to right, you are going uphill. This will indicate that in the direction of increasing x, f of x sub 2 would always be greater than f of x sub 1. Indicating the function to be increasing in this particular interval. If, however, it is observed that f of x sub 1 is greater than f of x sub 2 whenever x sub 1 is less than x sub 2, then f is said to be decreasing in this particular interval, as illustrated by this graph, where we observe that in the direction of increasing x, we trace the curve downhill, telling us that f of x sub 1 would always be greater than f of x sub 2. In this illustration, the function is said to be decreasing. But if f of x sub 1 is found to be equal to f of x sub 2 for all x sub 1 and x sub 2 in the interval, then the function is said to be constant. Okay, that will be illustrated by this graph here, where the blue graph is the function of y equal to f of x, and notice that in the direction of increasing x, y value or f of x value is held constant at a particular value, indicating that the function y equal to f of x is a constant function. Increasing or decreasing function or constant function can also be investigated using f prime value. So consider this illustration here, where we observe that the tangent lines drawn at points on the curve of y equal to f of x are noted to be with positive slope. This is the general observation whenever we have an increasing function. But if the function is decreasing, as in this case, where tracing the curve we go downhill, observe that the tangent lines drawn at points on the curve of the said function would always be with negative slope, and that in this case the function is decreasing. As to a constant function, the tangent line drawn at points on the curve will be observed to be horizontal, and therefore the slope is 0. So that we conclude that a function that is continuous in some closed interval AB and is differentiable on some open interval AB would be increasing whenever f prime is observed to be with positive values for every x in the open interval, and is said to be decreasing in the closed interval AB if f prime of x is less than 0 for every x in the open interval AB, and is constant whenever f prime is equal to 0 for every value of x in the open interval. Okay, though the sign of f prime would tell us whether the function is increasing or decreasing, it does not give us an idea of the concavity of the graph or the direction of bending. There are two ways at which we can characterize the concavity of a function. So let's consider having a differentiable function f defined on some open interval. Then we can characterize concavity of the function as follows. One is using f prime value, or looking at the slope of the tangent lines drawn at points on the graph. If the tangent lines are observed to be increasing, going left to right of the graph, then we say this graph is with upward concavity. Look at this illustration here. We have the black curve to be the graph of y equal to f of x, and at points on the curve we have drawn the tangent lines, and these are given by the green lines. Observe that going from left to right along the curve, observe that the tangent lines are with increasing slopes. On this side of the graph, the slopes are negative. Here it is 0, and over here with positive slopes. So we illustrate in this particular figure increasing slopes of the tangent going from left to right of the curve. The graph is said to be with concave up concavity, or the direction of bending is upward. A second way to characterize concavity of the curve is using f double prime, or the second derivative value, and whenever a graph is concave up, the second derivative value is said to be positive for every x value in an open interval. When the graph is with downward concavity, this is what we're going to observe. Consider the graph of some function as given by the black curve there. Going from left to right, observe that the tangent line drawn at points on the curve are with decreasing slopes. On the left side, we have the tangent lines with positive slopes. Over here, the slope is 0, and on the right, the tangent lines are said to be with negative slopes. So we observe that the slopes are of decreasing values. In this case, the function is said to be with downward concavity. And if we are going to make use of the second derivative value, then the second derivative value evaluated at any point on this curve will be with negative value, indicating a downward concavity. Another property that we need to consider would be the points of inflection of a given curve. These are points on the curve where the graph would be changing concavity, either from concave up to concave down or from concave down to concave up. Okay, looking at some illustration, consider this figure here. This point is said to be a point of inflection because we observe that on its left, concavity of the graph is downward, but as you move to the right side, concavity is upward. So at this point, we observe a change of concavity from downward to upward. Or we may have a case like this where concavity would change from an upward concavity to downward concavity going from left to right of the curve. To summarize what we have taken up in this lesson, first is that the first derivative value of the function evaluated at a given value of x would give us an idea of whether the function is increasing, decreasing, or constant. That the function is increasing if f prime of x value is found to be positive. It is decreasing if f prime of x value is negative, and is said to be constant if f prime of x is equal to 0. The second derivative value of the function will give us an idea of the concavity of the function, and that the curve of the function is concave up if the second derivative value is positive, and is concave downward if the second derivative value is negative. So that will be all for today. I will see you in the next lesson.